Hello everyone, welcome back to the channel. Today we are tackling a really interesting and tricky Leetcode hard problem, binary tree maximum path sum, problem number 124. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given the root of a binary tree and we have to return the maximum path sum of any non-empty path. First, let's define a path. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. So basically, it is just a sequence of connected nodes. A node can only appear in the sequence at most once. Note that path does not need to pass through the root. And the path sum of a path is the sum of nodes value in the path. And our goal is to find the largest possible sum in the entire tree. Now let's look at some examples to make this crystal clear. In example 1, we have a simple tree with 1 as a root and children 2 and 3. And one of the optimal paths can be to go from 2 to 1 to 3. And the sum of this path will be 6, which we return as the answer. Now let's look at slightly more complex example where we are given the tree with root as -10. Now what are some of the possible paths? Well, one path can be we just visit node 9 with sum as 9, or another path can be that we go from 9 to -10 to 20 with sum as 19, or another path can be that we go from 9 to -10 to 20 to 15 with sum as 34. But what about path 15, 20 and 7? This is also a valid path with sum equal to 42. And even though this path does not involve the root node, it is still the path with the highest sum in the tree. So for this example, we would return 42 as our answer. So by now, you would have noticed that the tricky part in this problem is that the maximum path sum can lie between any two nodes, and our algorithm needs to be able to find it no matter where it is. And one of the naive approach can be that we check every possible path, but defining every possible path is complicated. So a simpler but still naive way to think about this is to consider each node one by one as the highest point or the peak of a potential path, say starting with the root node. And what do I mean by the peak? Imagine we pick a node, say this node -10. A path centered at this node would consist of a node itself plus the longest possible downward path from its left side and the longest possible downward path from its right side. So basically, we will get kind of a V shape but upside down, where we go up to the highest point and then go down. And then we can start the algorithm by initializing a global maximum to a very small number or a negative infinity, denoting the maximum path sum we have found so far. For this peak node, we then calculate the longest path sum starting from this node and going down its left subtree. Let's call it left sum, and here it is 9 coming from this path. Similarly, we will find the longest sum path down its right subtree. Let's call it right sum, which we get here as 35 from this path. And it is critical to note that these left and right sums represent the longest path starting from the child and going downwards. They are not the longest path that may exist anywhere in that subtree. Why? Because we can't visit a node more than once. For example, the longest path on the right of the root node -10 will be this one, where we collect the nodes 15, 20 and 7, which will give sum as 42. But if we would have returned this from the right side, then we are visiting node 20 twice, because we go from 10 to 20 to 15 and then again come back to 20 and then go to 7. And a single path can't branch out from node 20 to 15 and 7 all at once. That would violate the rule that a node can only appear in the path sequence once. That's why instead we only find the longest path that start at the node 20 and go straight down. And here we have two downward paths to choose from. Either we go from 20 to 15, which gives us path sum of 35, or we go from 20 to 7 for a path sum of 27, and we simply choose the larger of the two, which is 35. And the total path sum with this current node as a peak will be sum of the nodes value plus the left sum and the right sum. So here this sum is equal to 34. And now initially the maximum sum was negative infinity. And since it is greater than our current global maximum, initially set to some smaller value, 34 becomes the new maximum. And we are not done yet. We have to repeat this process for all the nodes in the tree, because this maximum path sum can lie anywhere. And one more point to consider is, what if sum of the longest downward path on the left or right is negative? For example, suppose instead of 9 here we had negative 9, then the left sum would be negative 9. And if we include it in the path, the total path sum for minus 10 peak node would drop. For example, without the left path, the sum is minus 10 plus 35 equal to 25. And including the left sum, it becomes 16. So whenever we see a negative left or right sum, we should ignore it. And programmatically, here for left sum, we can take maximum of 0 and negative 9, which gives us 0. So we get a better path by cutting off that negative branch. And now continuing with the example, we are done with node minus 10. So we repeat the process for next node. Say we go in a pre-order traversal, where we go to the root, then left and then right to select our peak nodes. So now node 9 becomes the peak element, and for node 9 both left and right sum will be 0, and the path sum will come out to be 9, which is not greater than 34. And then we move to the next node, which is 20, and here we see the left sum will come out to be 15 and the right sum is 7. So the total path sum centered at 20 will be 42, which is more than 34. So we will set our maximum to now 42 and move to peak node 15, where left and right sum are 0. So the path sum will be 15, which is not greater than 42. So global maximum remains 42. And finally, we move to node 7 as a peak, where again the left and right sum is 0 and path sum will be 7, which is again not greater than 42. And in the end, the global maximum remains 42, which we return as the answer. Now, this approach is correct, but the time complexity of this approach is O of n square, where n is number of nodes in the tree, because we traverse through all nodes in the tree, and then for each node, we traverse all its descendants to find the longest left and right paths. And in the worst case of a skewed tree, this may result in the time complexity of O of n. Hence, the overall time complexity will be O of n square, and the space complexity will be O of h, where h is the height of the tree, mainly dominated by the recursion stack of the traversal. And in the worst case of completely unbalanced tree, the recursion depth will be n, resulting in the space complexity of O of n. And the problem with the naive approach is that it does a lot of redundant work. We are basically recalculating left and right downward path sums in subtrees over and over again. And this restarting of the downward traversals is the bottleneck. What if we could get all the information we need in just a single traversal of the tree? And this is key to solving this problem efficiently. In naive approach, we were covering all the nodes and we used pre-order traversal there. But we could have used any traversal for covering all the nodes. But if we have to get the longest downward paths, why not start from the leaf nodes? For example, for node 15, we know the longest downward path starting from it is 15 itself. And similarly, for node 7, it will be 7. And then when we come to the parent, which is node 20, we already know the answer from its children. And we can see that the longest downward path starting from it is 35 by going to the left. So by going upward, processing children first and then going to the parent, we calculate each downward path sum only once. And basically, we are doing the post-order traversal. So now our recursion function, let's call it DFS, has two jobs. One is to calculate the answer, which is the longest sum when the current node acts as a peak node, where we add the left sum, the node value and the right sum. This is like the upside down V-shaped path. And then we compare it with the global maximum, which is returned once all the nodes are processed. And this is very similar to the naive approach. But now it also has a job 2, which is calculating the longest downward path starting from the current node. So instead of calling a separate function like we were doing in the naive approach, now our recursive function has to do that as well. And typically a function takes in few inputs and return only a single result or output. But here we want two outputs. So one nice way to handle this will be to return the longest downward path starting with this node as the output. And now using this, we can call the function with the left and right children and get the longest downward path on the left and right and calculate the path sum by summing these values and the node values, which is the answer we needed, and update the max value from it. And for the max value, we can use a global variable or pass it into the function context again and again. So any of the solutions will work. Now let's quickly see this in action. So again, we start with the root node, and to calculate the longest path on the left and right, we recurse down the children, which are 9 and 20. Say first we go to the left child, where we see node 9, and again to calculate the left and right sum, we recurse to its children, which are both null, and here we hit the base case. When the node is null, the longest depth starting from it will be 0. So both left and right sum will be 0. And now first we look at the job 1, which is to calculate the maximum path sum with the current node as the peak node, which we calculate as node value plus left sum plus right sum, which will be 9 plus 0 plus 0 equal to 9. And since our global max is initially negative infinity or not set, the new global maximum is 9. And now comes the job 2, where this function returns the best straight path it can offer its parent. And since we are returning the straight downward path, this node will be just a continuation of the path upwards, and hence we should add the node's value to the better of its two child paths. So we sum up 9 with the maximum of 0, 0, which will be 0. So we return 9. And now we are done with the whole of the left subtree and continue with the right subtree, where we come to node 20. And to calculate the longest downward path for it, we have to recurse down, say to the left child first, where we see node 15. And again, to calculate the longest downward path, we recurse down further, where both the left and right child for it are null. So we get 0 as left and right sum from both the sides. And now for job 1, we calculate the answer, which will be 15 plus 0 plus 0 equal to 15. And since it is more than our current maximum path sum, we update the maximum to 15. And then comes the job 2, where it has to return the value to its parent, which is 15 plus maximum of the left and right sum, which is 15 itself. And similarly for node 20, we will process child 7. And again, since both of its children are null, we will get left and right sum as 0. And then we do the job 1, which is calculate the answer, which will be 7 plus 0 plus 0 equal to 7. But since 7 is less than the current maximum path sum, which is 15, the answer doesn't change. But in any case, we still need to do job 2, which is return the longest path sum with this node as a continuation, which will be 7 plus maximum of 0, 0. So we will return 7 from this path. And finally, we come to node 20, since both its children are processed. And for it, the left sum is 15 and right sum is 7. And again, We first run the job 1, which is to calculate the answer with 20 as the peak node, which will be 20 plus 15 plus 7, which is 42. And this 42 is more than the current maximum. So now the maximum path sum becomes 42. But it still has second job to run, which is to return the maximum downward path sum with this node as a continuation. And it will be 20 plus maximum of 15 and 7, which is 35, which it returns to the parent. And finally, since we are done with the right subtree, we go back to its parent. And again, we run the job 1, which is to calculate the answer. And here it is minus 10 plus 9 plus 35 equal to 34. And since this answer is less than the current maximum, the global maximum remains 42. And then we perform the job 2, which is to return the longest downward path with this node as a continuation, which is minus 10 plus maximum of 9 and 35 equal to 25. And now, since we have covered all the nodes, we are done. And our answer, which is maximum path sum, will be 42. And now, the time complexity of this approach is O of n. Since we are visiting each node exactly once, and the space complexity will be O of h used by the recursion stack, which in the worst case of unbalanced tree will be O of n. And for the balanced tree, it will be O of log n. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. First, we initialize our answer, that is the maximum path sum, as a global variable to a very small number, which is integer.minValue in Java and negative infinity in Python. Now our main function simply kicks off the recursive DFS call starting from the root of the tree, and after the DFS is complete, the answer variable will hold the final answer, which we just return. Now let's look at the DFS function, which does all the heavy lifting. The first thing we do is handle the base case, which is if the node we are looking at is null, it means we have reached the end of a branch and it can't contribute to any path. So we simply return 0. Otherwise, we make two recursive calls, one to the left subtree and another to the right subtree. And this is the post order traversal, as we are going all the way down before processing the current node. And the result from these calls return left and right sum, which represent the best possible straight line path we can get from the left and right subtrees. And crucially, we wrap these results with maximum of 0 and the resulting value from the recursive call. This is our trick to handle the negative paths. If a subtree gives a negative path sum, we are better off not including it at all. So we treat its contribution as 0. And now that we have the best possible downward paths from the children, we can simply perform the job 1, which is to calculate the maximum path sum with the current node as a peak. And we calculate this by adding the node's own value to the left and right sums and compare this V-shaped sum to our global answer and update the answer if it is larger. And finally, we perform the second job or action, which is returning the value this node can offer to its parent. And remember, this has to be a straight line path. So we return the node's value plus the larger of the left or right sums, and this value gets passed up to the recursion chain. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.